we talked about this address being arbitrary in memory, and I kind of plunked the memory location down here in an arbitrary way. The 50 is just sort of at the bottom of the screen on the right hand side. But actually, the hexadecimal location of the memory address is also arbitrary, and it depends on things like how much memory there is and where else the memory is. It turns out that C has two different operators that let us C, that I use C here in the double quotes kind of way. We don't actually see it, but allows us to access addresses where variable values are stored. And in other words, it lets us address, rather than the metaphor of a post office box number, it lets us access the actual address in memory. And we have two operators here. The ampersand, the and sign, is, let me turn on my pen here. Usually this takes a second to work. There we go. Now this is what is referred as the address operator. We have used it before as in a logical way as the and sign. And what this does is it is a way to notate the actual address in memory. So it lets us access that. The asterisk or star is called the dereference operator. Now, a dereference operator, what does that do? What this does is it actually stores the address of a variable in memory. So it actually stores it. And we're going to be talking about how to use both of these. And this is a topic that can be potentially confusing when you first encounter it, but it's one that we're going to stick with for a couple of weeks. So it's very important to get the ideas. And we're going to talk about it a lot and have a chance to talk about it. And all of the programs and notes go through this in explicit detail. If you're just encountering these ideas for the first time in the computing world, you're probably going to need to use all the resources and maybe discuss it when you're working on your problem sets. Okay, so we're just really starting that now. Now, the thing we're talking about today is has to do with pointing and manipulating and making good use of these addresses where something live. And we actually have a name for these operators like this, and we call them pointers. Okay, so the pointer is essentially an address, or it itself is a variable. Now it's separate from a variable that holds a value. This variable holds the address, and this becomes an interesting and powerful concept, it turns out, in the basics of computing. It really is going down a level from just telling the computer what to do with some script, and it gives you a deeper understanding of how the script actually works to make the computer work for you. So what does this look like? Maybe we, and again, here you're going to want to look at the addresses code. There are a couple of versions, 2 and 3. Put that in squiggly braces because they can take different values. So make sure and look into these to see how this works. Here what we've got is we've declared and initialized a variable called in, and then we can declare a new variable. Notice we're using the dereference operator, and we'll call this one P, and this is a pointer. And here we're storing in the pointer the actual address of the variable in. Okay. Say a few things about this. That, I mean, we're using this extra notation to lay out a system where the asterisk P, the pointer, stores the address of the value of in. It's the address of the value of in. It's kind of awkward. And it's also kind of archaic by modern programming language standards if you've used Python or something like that. The thing is that it's very explicit, and it allows us to get some insight in what's actually happening here. If you mess around with the addresses code and you compile it and run it, what that's going to do is it's going to print out the address of the variable that you create, and you're going to get some value that's going to look something like this. And we know it's a hexadecimal number, but boy, is it big. Why the heck is it so big? Well, it's big because memory is real big these days. If you're lucky, you've got a laptop with at least 8 gigabytes of RAM. And these days, if you specifically have something to do data science, you're probably going to want something that has at least 16. R, the program R, one of the programs I use a lot for data science and data analysis, is limited in the amount of data it can store natively to 2 gigabytes. But, you probably have access to a lot more. Maybe even 64 for a workstation, or 128 gigabytes of RAM, depending on what kind of work you do, of course. All right, so the hexadecimal number has to be big to account for all the places that are available for storage, the bigger and bigger your memory is. So we've got, here's what we just kind of saw if you ran through that addresses code. We've got your memory. We've stored some value in memory. That is allocated to have a hexadecimal address. And then we're going to use a pointer that stores the value stored in the pointer is itself the hexadecimal address of the actual value of the variable the pointer is pointing to. All right. Now, what is actually happening here? We've got this 50, we've got the address, and we've got 4 bytes of information. It turns out the pointer is actually pointing to the beginning of that where those bytes start in memory. This is an important concept because guess what? This also applies to strings. And we're going to revisit strings. We've been using, the kind of training wheels functions for strings. And we talked a little bit about this in earlier weeks. And, it's just best to use the CS50.h and the string headers. But actually, what a string is it's an array of characters. Okay, so this is important for pointers. So if we have this string that we call S, and we're going to store the characters HI exclamation point, remember we actually store this in different units. And there's one extra than the 3 characters, and that's the null character \0 at the end. Of course, we can come up with a notation for the string itself, the string array. But now we know that each of the, this address, this is sort of like the post office box addresses. So this is the metaphor way of thinking about this. And we can actually reference that in our computer code, of course, to directly get to those places where our variable's stored. But now you should be able to expect that those addresses each have hex reference addresses that tell exactly in memory where that is. So, if we had a pointer to our string, it would store a beginning address like this. And, notice that the address that we're looking at is actually pointing to the very first starting point of the character string. So, this is demonstrated in addresses 4 and 5.c in the notes. So you want to take a look at those. Now, we've used printf a few times. Whoops, that should be a T. We've used the printf function to print character strings a lot of times by now. And what's actually happening is that the printf starts reading the array, and it reads one character at a time. So it would use the address, and it would keep going, and actually it would stop when it gets to the null character. And I just want to say here at this point, I might reiterate this later, that nobody actually cares about what that address really is. Nobody actually cares that this might be 0x123. Who cares? I don't care where it is. It's arbitrary where that's put in memory. I could care less. What we do care about, however, is we do care about using a function like printf and being able to get to that place in memory in a memory efficient and fast way and reliable way. And that's where the power of this comes. So, we might declare a string like this, and this is using the class string. That's what we've done up to now. And another way to do that, the way that doesn't use training wheels, is to declare our character string by now using the C native. We don't need a header for the char data class, or char data class that's already in there, and we use a pointer to denote the starting place of memory for our string. So we've just declared a char, designated the pointer, and notice the notation here is asterisk and the name of the pointer, which we'll call S for string, and with no spaces. Now this, if you look in addresses 7, and run this, you'll see that some code that exploits this way of declaring a string. And this is like dropping the training wheels. Now, this is the way we would normally do it in C code. It's just an address. And the string S is really the same as char asterisk S with the pointer notation. Yeah, so what is string? Well, it's the type that has been defined for you. We made our type with the struct and the type declaration, and we declared strings for our phone book, and we output and defined the different kinds of data in the struct as a person, which we can access. That's what we did last week. And the different parts of this program we already talked about, but we exploited the type def to define our own kind of data structure here. Interestingly, type def is super powerful, but we could alias the integer to be an int. We could call it another name. I don't know why we might do that, but it's possible. but we also likewise for a string, we could use a pointer. We could use a pointer just like that, and we could call our pointer a string, and guess what? That's exactly what the string function does in the cs50.h header. Now this has some simplifications, different functions that were in it while you're looking at different concepts. And before we got to some of those concepts like pointers, like we're covering now, but like I said, it's always an option for you to use these in this course, but you will want to wean yourself off of them, and will have to do that explicitly for the problem sets for this week. Now, we can also do some arithmetic with pointers. This is kind of interesting. And if you want to follow along with this next little bit, it's in the code addresses 8, 9, and 10.c. So now what we can do, what you'll see when you go to these programs, is that we can exploit the starting place of a pointer, and we can actually use some notation like +1, +2, etc. to move through the character array to access different starting points or different elements in the array. So we'll start off with some ints, and we're moving to a different program now. The program we're moving to is compare.c. So the idea, this is one of the first real explicit examples of the power of a pointer that you'll see. So maybe we have maybe you have these two variables stored in variables I and j. They're both integers. They're both of the same value, 50. But you can try out the program to try different values for yourself to see what you get. But up to now, if we were going to compare these values, we use the strcomp. And like I said, this is in the compare versions of C, compare 0, compare 1.c, and compare 2.c. But we're going to move from using strcomp to figure out exactly what's going on and what pointers have to do with it. So, so our memory, we've got a string that we call S, and it's got some address in memory. Now the string itself, the character array, is stored elsewhere, and in S, the pointer S, we're just storing the address of it. So we've got some addresses of where our string starts. Again, the memory, the actual place for the memory is arbitrary, and the starting address is 0x123, and so our pointer to the array is 0x123. Well, likewise for our if we wanted to compare two character arrays, we need a different pointer, and we'd have a different array, and if they were both declared, even though they contain the same value, they would be located at a different arbitrary address. And in this example, the second character array starts at 0x456, and so our pointer t would have the value 0456. And we could kind of think of it like the two pointers are pointing to the beginning of those two different places in memory, even though they contain the same values. So we could do this differently. Here's a new program that you can look at and follow through with the notes. It's called copy.c, C-O-P-Y.c. And for this one, we've got the same kind of setup where we've got a pointer, We've got a character array. We've got some addresses for that character array, and the pointer holds the address of the beginning one. We've got a second array. Now for these examples, we set t to the value of s. And what's happening with arrays when we do that is something different than if we set t a value unto itself. Here, the pointer value for t, because we set it to the value of s, would point to the exact same place in memory. And this is what's happening in the strcomp header. When t is a copy of s in the memory address, it's recycled. The memory is recycled. Well, in this world, this all makes sense, and we've had the luxury of the memory we've done up to now by virtue, in part, of some of these helper functions in the header files that we've been using. Any considerations for how much memory we need to set aside for this stuff has been done for us. But we actually need to talk about some ways to do this explicitly. This is getting down to the nuts and bolts of what making a computer work for you really is and really does. So in the next couple of examples, this is sticking with a copy. It's copy 2, copy 3, copy 4.c. The point here is that the memory allocation is important. And we've got a couple of functions to introduce here. We're going to use both of them in these copy examples and in the notes. If you make a new variable, you need to allocate the memory for it. And malloc stands for memory allocation. And we would typically use malloc to set aside the space for explicitly for a variable we're declaring. Now, up to now, this has been done for us in some of those helper functions, but we're going to start doing it. And free is a way to free up the memory when you no longer need it when your program finishes. So the code demonstrates the use of malloc in the notes. Go through those examples. So we've got our pointer. It's pointing to a character array. We've got our other pointer, t, and it's pointing to a different place in memory. And what is happening in some of those programs is we're reading the character array one character at a time, and we're writing it in memory. Now, if you change the case in S, T has its own memory, and it won't be changed. And another point to make here is that the way that memory is read in a character array is one space at a time, one memory unit at a time, usually until it gets to the null value. So in copy5.c, you can see some ways to poke malloc with a sharp stick and make it fail. Now, you can do an error check with the memory that you're doing, and you'd want to do that to avoid certain problems. Like one problem would be what is referred to as a memory leak. What is a memory leak? Well, a memory leak is when you ask for memory and you do it in a way where your program iteratively asks for more and more memory without freeing up the old memory, even if you aren't using it anymore. This is called a memory leak, and it causes crashes and can cause very big problems. We'll talk about one of those later. Sometimes it's nice. The point here is sometimes it's nice to just, hey, let me double check my program to see if there are any memory problems or memory leaks that I need to pay attention to. How do you do that? Well, there's a tool at the command line called Valgrind. that you use when you're executing your program, and you get a series of messages that we go through in the notes in some detail about the memory usage in your program. So you're going to want to play with that. And for this, you're going to want to look at the file memory.c in that section of the notes. All right, so what Valgrind allows you to do is to find bugs. It allows you to find maybe there's no zero index, and so it creates a memory leak, or you don't have the use of the free function to free up memory when you're no longer needing to store a variable, that sort of thing. So you can test this out yourself with your own code, and as you'll see in the notes, you use this by invoking the little program at the command line, and then going ahead and invoking your actual compiled program. That's the use of it. Now we're going to introduce here the kind of concept of garbage values. What are garbage values? Well, garbage values are the remnants of something that was in memory that we don't need anymore. And you can actually, if you look through the notes and go through the go through the garbage.c program, you can actually find garbage values on the computer that you're using by just paging through them. And I think the program has you do it for 1,024 of those values or something. And what you can do, I think this is in the notes, is that when you run garbage, you can use the pipe operator and use the flag less, and the pipe less paginates the output in your terminal. So if you have 1,024 values, it might just show you 20 at a time, so you can scroll through them faster. Now we're going to be looking at programs that use these pointers quite a bit, and you'll, I hope, start to see how useful they are. So you can declare a pointer. We might declare pointers for X and Y, and we can allocate using malloc some allocation of memory for a variable called X. It would be stored at the address at the pointer to X, and here it's just being initialized with using a function called size of, and here we're specifying it's the size of an integer. So we're explicitly saving out 4 bytes worth of memory to hold our integer that we're going to do. What this tells you to do is to go to the address for X and store the value 42 in it. And now we've got the pointer to Y, where we store 13 in it. And essentially what you are going to look at in the program is how garbage values interact with that. If we set the value of Y to X, and then we take the pointer to store a new value in it, then we're fine. Okay, so you need to look in the notes and run the programs to experience that. So pointers are kind of hard. A lot of people find them hard. I certainly found them confusing when I first encountered them. They really are one of the important concepts to wrap your head around, and we're doing it in, I think, a pretty humane way. We're just going to watch a little YouTube video here.
Hey, Binky, wake up. It's time for pointer fun. What's that? Learn about pointers? Oh, goody! Well, to get started, I guess we're going to need a couple pointers. Okay, this code allocates 2 pointers which can point to integers. Okay, well, I see the 2 pointers, but they don't seem to be pointing to anything. That's right. Initially, pointers don't point to anything. The things they point to are called pointees, and setting them up's a separate step. Oh, right. I knew that. The pointees are separate. So, how do you allocate a pointee? Okay, well, this code allocates a new integer pointee, and this part sets x to point to it. Hey, that looks better. So make it do something. Okay, I'll dereference the pointer x to store the number 42 into its pointee. For this trick, I'll need my magic wand of dereferencing. Your magic wand of dereferencing? That's great. This is what the code looks like. I'll just set up the number and... Hey, look, there it goes. So doing a dereference on x follows the arrow to access its pointee, in this case to store 42 in there. Hey, try using it to store the number 13 through the other pointer, y. Okay, I'll just go over here to y and get the number 13 set up, and then take the wand of dereferencing and just... Whoa! Oh, hey, that didn't work. Say, Binky, I don't think dereferencing y is a good idea, because, setting up the pointee is a separate step, and I don't think we ever did it. Good point. Yeah, we allocated the pointer y, but we never set it to point to a pointee. Very observant. Hey, you're looking good there, Binky. Can you fix it so that y points to the same pointee as x? Sure, I'll use my magic wand of pointer assignment. Is that going to be a problem like before? No, this doesn't touch the pointees. It just changes one pointer to point to the same thing as another. Oh, I see. Now y points to the same place as x. So wait, now y is fixed. It has a pointee. So you can try the wand of dereferencing again to send the 13 over. Okay, here goes. Hey, look at that. Now dereferencing works on y. And because the pointers are sharing that one pointee, they both see the 13. Yeah, sharing, whatever. So, are we gonna switch places now? Oh, look, we're out of time. But...
Okay. Now that cartoon, that claymation, demonstrated the exact concepts we've gone through in a, I hope you found, mildly humorous way. Now, a lot of the, when we were talking about algorithms last week, a lot of the demos we did involved swapping values. And basically, the way that the swapping works, let me just turn on my pen here, go back a page. The way swapping works is, say we have a vessel that contains y and the other one contains x, and we want to swap the values. The concept we're going to demonstrate here is such that we can't take y and put it into x, because that would either destroy x or mess up the values, and we can't do the reverse. And so from a memory perspective, we need some kind of way to create a temporary holder for a value. And so if we wanted to swap y and x, we might take x and put it over here. That would allow us to take y and put it directly into the vessel that X used to be in. And then I have to get faster at invoking my eraser here. And then we can quite easily take X and put it in here. So that's kind of what we're going to talk about. To follow along with this in the notes, you're going to want to start with a series of swap scripts. So swap 0 is the first one that looks like this here on the left. Now, what the code in that little script will demonstrate is that the successful swap in a local function doesn't affect the global variables in a main that might be wrapped around this. And so because of that, using a function like this doesn't work. And the lesson here is that we need to be aware of a local versus global scope. Now, we talked about this in some of the tutorials and lectures over the last couple of weeks. But just to remind you a little bit, in case it's useful, something is local if you declare and initialize a value inside of a function here, and it's global if it's a variable that's declared outside of a function, so that in, for example, the main part of the program, the variable's declared and can be affected. So the lesson here is we need to beware the local scope. So this is just an issue to be aware of. Now, we can pass copies of values when we do this. When we're doing a swap, for example, we're not actually changing the value or passing explicitly the value that's stored in one location. We're actually copying the value and passing it to a new place. So we're making a carbon copy of it, sort of. Again, we're thinking about memory and the chip on memory and our little spaces to store values and variables. And then we don't really need to think about the chip much anymore. We don't even really need, for this example, to think about the spaces on the chip. So we're going to really generalize our notion of what memory is here. And we think of all the memory that's available in a computing operation. When a program is first invoked, the topmost, and this is sort of metaphorical, the topmost amount of available memory is where the machine code is stored. Okay, so the machine code is the zeros and ones that your compiled program is comprised of, right? So what's just below that? Well, what's just below that are any global variables that are loaded. They're loaded lower down, and if we use malloc explicitly in C or implicitly in other kinds of languages, then that memory, those locations are stored in an area called the heap. Okay, so the heap fills in a downward direction. Now, in a previous tutorial, if you I think it was last week, so for week 4, we talked about the notion of the stack, and stacks grow upwards. So the opposite of the way that heaps grow. And we talked about the stack a little bit. You can actually use the swap 0C program to kind of look at this, where we've got our main chunk of memory in our stack, and then our swap function gets added on top of that. And, we might have our variables. They might have some values. We've got our program invoked, and we're storing the locations of those, A, B, and a temp to execute the swap. So we store the values of the variables at the locations 1 and 2. And if we go through what's actually happening like we would in something that's stepping through the instructions in our program in order, if we store the value of A in temp, our stack now looks like this, where there's a 1 in the temp location, and then we're changing A to the value of B. Now A becomes 2, and now B gets changed to the value of temp. So that's actually what's happening there. And, that's what we were doing in those swap functions last week. So we have a bit of an issue with passing by reference, and this is the scope kind of issue, where because we want to execute swap to affect variables in the main program, we can't execute these operations directly with the variable names because they're only local in scope within the swap function. So what we actually need to do, here's where the power of the pointers really comes in, is we convert the swap program to be comprised of pointers itself. And here we're doing that thing that we called passing by reference. So we're passing the value of variables to a reference of the variable rather than the variable itself, and we avoid the problem of scope by doing so. So here, if we go through this function swap, same way we did last time, got our variables like before, but here we're passing by reference, and if we step through our value like before, when we set temp equal to the value that's at the address of A, temp becomes 1. The address of A, the pointer of A, gets set to the pointer of B, and you can see how that affects the values. And then finally, the pointer for B is changed to the value of temp. So it's fundamentally different. We fix this program, we fix the problem of scope by dereferencing our call. Now there's a problem. You will have heard of this problem before, that if we look at this model of how our memory goes, you can run out of memory sometimes. And the places where you run out are the places in a program that fill either the heap or the stack. And, if you run out of memory in the heap, that's called heap overflow. And if you think about the name of that famous website, if you run out of memory in the stack, that's called stack overflow. And, this is like what happens commonly in programs that don't manage their memory correctly. And, sometimes you have a buffer that's set for overruns, but you can actually have a buffer overflow as well. And you guys might remember, I think it's been around 6 months ago, that there was this company called CrowdStrike that had such a problem. They had a buffer overflow problem, and globally, companies like airlines and transportation companies were using the software, and they had an automatic update, pushed an update with this buffer overflow problem, and it shut everything down. And this underscores why this is such a big deal. We're going to watch a little program here about that. Just going to bring up the old YouTube. There we go.
The largest IT outage in history? Yes, the CrowdStrike outage on July 19, 2024 was one of the largest IT outages in history. Some called it a real manifestation of the fears that computing users had at the end of the last century with the Y2K bug. Here's what happened. CrowdStrike, a security vendor offering the Falcon platform used by Microsoft and other companies to minimize cybersecurity risks, released a configuration update that contained a logic error, causing millions of Windows devices to crash. To learn more about the error and the specific causes, click the link above or in the description below. And please remember to like this video and subscribe to Ion Tech for more business technology videos. According to Microsoft, approximately 8.5 million devices were directly affected. While that's less than 1% of Windows-based machines worldwide, the systems affected were running critical operations. Airlines were majorly affected, including Delta, United, and American Airlines. They were forced to ground, delay, and cancel more than 10,000 flights worldwide. Healthcare companies faced disruptions in appointment systems, while some states reported 911 emergency services being affected. Multiple broadcast outlets were taken off the air, including Sky News. Online banking services and financial institutions were inaccessible. And public transit systems in Chicago, Cincinnati, Minneapolis, New York City, and Washington, D.C. were also affected. While CrowdStrike was able to identify and deploy a fix for the issue in 79 minutes, the recovery process for businesses is extremely time-consuming. Among the issues, with the problematic CrowdStrike update installed, the underlying Windows OS could trigger the dreaded blue screen of death, or BSOD, rendering the system inoperative using the normal boot process. In this case, IT administrators have to manually boot affected systems into safe mode or the Windows recovery environment to delete the problematic file and restore normal operations. In some cases, the process also requires physical access to each machine affected. It is estimated that it could take potentially months for some organizations to entirely recover all affected systems from the outage. Were you affected by this outage? Share your experience in the comments below and remember to like and subscribe too.
Well, there you have it. Were you affected? It's actually longer ago than I thought. It was a little bit more than a year ago as of the time that I'm recording this. Okay, let's go back to the slides here. If you download the lecture slides, by the way, you can get the link to the outage there. Okay. Now this next slide, I think, just talks a little. Oh goodness! Stop that. No ads. Come on. There we go. The next slide just gives a little bit of an outline about some of the technical aspects to the CrowdStrike update failure, which I'll let you read if you're interested in this. But one of the details that's relevant to what we were talking about today is that it expected this overflow of memory. It expected only 20 values, but there was an attempt to access a 21st value, which was an out-of-bounds memory read. And that's what resulted in the crash. Made me laugh a little bit that they were talking about Windows systems and blue screen of death. I do use Windows myself most of the time, but there you go. One of the things I just want to reiterate is that we've been using these I don't want to call them training wheels functions because they are quite useful. But what they are is functions that have, they gloss over some of the nuts and bolts of things like memory allocation. For example, when you swap, when you're doing a swapping operation, or the character versus string functions, and these all manipulate user input, the get functions that are in the CS50 header. And we talked about getInt that grabs an int from a user. And the idea here is that, how do you actually allocate memory for this, or how does the getInt function actually work and store the input in memory? Well, we're going to explore the scanf function. And remember what we called these garbage values in in memory. So we assume that there's stuff in memory. Actually, when you do a hard formatting of a hard drive, all of the sectors that are available in memory are written usually with something like zeros. And so that could be garbage memory, or it could be something that was the memory space was previously used for, that's still there because it hasn't been explicitly overwritten with zeros. So when you claim a little part of the memory space, you're overriding garbage values, right? So the program that you're going to want to go through with the notes are the get programs. Let's see if I have my pen here somewhere. I'm just going to draw this in between. Do you guys recognize who this character is? So maybe you want to try all of the get programs, but get2.c is one that demonstrates the garbage values. This is Oscar the Grouch. He lives in a garbage can. He's one of the Muppets. He was famous on Sesame Street, if I didn't mention that before. So maybe there's a block of memory that is pointed to by some pointer. And it's pointing, if you don't overwrite what's in the pointer, it's just pointing to garbage. And, we have to tell that pointer where the value is that we're pointing to. And, when we block off a set of memory amongst an array of garbage, it might look something like this, where if we use the function getInt, for example, it allocates just enough memory plus 1 for possibly an escape character, and the little program, the script get3, will demonstrate that for you. You can try it yourself. Now, I'm not going to say it's the last thing we're covering today, but I think it might be the last substantial thing we're covering is file input and output. This is going to start being important for your problem sets. There are a whole bunch of super useful functions to use, and there are things like file open, file close. That's fopen, fclose, fprintf, fscanf, where we scan through the contents of a file, fread, fwrite, fseek to look for something in. And when we're looking at at these functions, there's a series of demonstrations in the phone book files. Let's just give my pen a second to catch up. There we go. It'll come back in a second. There we go. And oh gosh, this is in the phone book scripts, so you can check out the first couple to demonstrate these concepts. All of these, like I said, are functions related to files. Now you're going to want to experiment with the code to look at some of the functions. One thing that I wanted to mention is that when you're doing operations on files, the way that C handles the operations. It's a little bit like handling character arrays or a YouTube video where it handles operations sequentially with reference to the content of the file. And one of the things we're going to learn to manipulate in files are bitmaps. It's one of the first things I mentioned with these slides. So a bitmap is a picture of anything. And when these files are read, the pixels from the are read from the top to the bottom and from the left to the right. So one whole row at the top will be read, and then the second row will be read, and it'll continue downwards like that. And one of the neat things that we use every day on the web, and if you are creating or doing anything to your own images, you'll already know all about this stuff. It's quite simple, but we're going to actually delve into what the computer is actually doing when it takes an image like this, and let's say that it removes all of the color information and retains only the black and white values. This is grayscale. Or maybe we want to look at sepia. Or maybe we want to flip the image and just reverse the direction of some of those pixels. Or maybe we want to blur, which averages adjacent pixels across the image. And maybe we want to do something like edge detection. So these concepts will be important for the assessments. If you read through the notes and run those programs, you'll be completely prepared. And the notes and guidance for the assessments themselves are very, very informative. You have to read them carefully, and we'll do that in class this week. And I'm going to end with my very favorite web cartoon, XKCD. I hope you guys know about XKCD, and it's a pointer joke. And now, I hope, after this lecture, you get it. And with that, thanks a lot, guys. Talked a lot about pointers, but that's all I have to say about that. I'll see you in class next time.